So this talk is called The Future of Scientific Code in the Era of Generative AI. It's a fairly grandiose title, but I hope that, this will kind of prompt interesting and relevant discussions, maybe discussions people are already having about how coding is changing in scientific work. So quick, short about me. This is like a homecoming because I got a really wonderful education at the University of Washington studying auditory neuroscience through computational methods. After that, I went and worked as an open source software advocate at Data Version Control. And now I'm a lecturer and researcher at the University of Michigan. And all the work that I'm going to show you was made possible thanks to funding from the Alfred P. Sloan Foundation. As you might know, code powers science research, and that includes data generating simulations, so a lot of classical numerical methods to simulate physical systems, data collection. A really big change that's happened in the area of research that I'm from over the last couple of years is we are increasingly seeing a lot of browser-based methods for data collection and behavioral experiments. Statistical modeling, whether you're doing classic inferential statistics, machine learning, statistical modeling is often implemented through software and visualization. And that includes not just our end product visualizations, but all the visuals that we make as diagnostics about our data and our software as we work. So now we have code LLMs on the scene, and I'm going to use the umbrella phrase code LLMs to refer to basically any kind of large language model LLM that could be used as a programming assistant. So that could range from somebody using ChatGPT on their browser to a dedicated plugin in their interactive developer environment. Pretty big range of tools here, but the kind of core building tools around large language models is, really what's at the heart of what we're going to discuss. So there's a big allure to code LLMs. Scientists are often undertrained as developers. This is very well known, even though coding is absolutely integral to much research. Even research that we wouldn't consider computational in nature still often requires coding on the part of the scientist. Many programmers across a range of user studies from the human-computer interaction literature studying programmers really seem to like using code LLMs. People generally are positive about their experiences and find that helpful. And if coding is an important part of our jobs, then of course tools that make it more enjoyable are of broad relevance and interest to us. There's also risks that are surfacing. One of them is that understanding and debugging code that you didn't write is hard. From the literature on how programmers learn, a really important part of being able to debug code is being able to form a mental model of what code does. And it's much harder to do that when it's about code that you didn't actually write. There are still major issues with inaccuracies in code. So if you ask a model to suggest code for you, there can be issues and it doesn't do exactly what you think it does or what you meant it to do. And also, if you ask it to explain code or why something works, there can be issues in the explanations. And these are still pretty noticeable for a lot of programmers. And scientific settings rarely have systematic code testing practices in place in the first place. So in a lot of industrial settings, it's very common that there will be a suite of automated tests that give you immediate feedback on, did you break anything unintentionally in your code when you made a change? And in scientific settings, we often work by fairly different culture standards, different infrastructure, different resources, and we don't often have this kind of really regimented, standardized quality control. So there's possibly more issues with, if a bug is injected somewhere, do we have infrastructure to catch it? So I'm going to present a couple studies that kind of over the last year or two have looked at what is going on with scientists and how they're, relating to and interacting with code LLMs. So I'm going to present first a survey that was conducted last year, trying to get at just a big picture. What is going on? What is the current state of code LLM use among scientists who program? So this is a survey that was conducted in July of 2024. I was trying to find out who is using, these tools and what tools are they using. So the inclusion criteria was someone who works as a researcher at the University of Michigan. I just sampled by job codes, so people whose job codes indicate that they are a researcher. And that could include students, staff, and faculty. And then I was looking for people who program at least regularly for their research, so they have to program in any language at least some of the time. And also this is for people who admit that they use a code LLM at least sometimes. So this is not studying people who don't do it. We're selecting in for people who are already at least sometimes using a code LLM. And so we have 199 responses from this, and this is all at the University of Michigan, a university which has a lot of similarities in its makeup to the University of Washington. But of course, that means that there's also limited generalizability to other types of universities. So the first finding is that chatbots are really king. People really are using chat interfaces, things like ChatGPT or Claude, and not, so much these tools that are plugins for your developer environment, like GitHub Copilot, which is an autocomplete that works in VS Code as well as now a couple of other developer environments. We're really seeing a big, trend towards people preferring to have a chat interface, like a natural language chat. And that's kind of stark because of the industry standard for software developers is pretty much all on integrated tools that are doing autocomplete or, or maybe a couple other modes of interaction, but it's not dominantly chat GPT. And one reason that I have some concern about this is because of if you've ever compared using something like ChatGPT to a kind of model that just suggests autocomplete, as you go, how would you complete maybe a line or two of code? Chat tools tend to generate much longer code suggestions. So if you're using something that autocompletes just a little bit, it will usually kind of self-truncate, within a couple lines, but you can get much more code at once out of ChatGPT or similar. And so this seems, and I'm certainly not the only person who thinks this, but this seems like it's quite a bit of burden on the user. If it's giving you more code at once, that's more code that you have to visually inspect or test in some way. And that is probably likely to be increasing the cognitive load of inspecting that code, although I have no empirical measures of that, that would be quite interesting to find some ways to measure. Another finding is that most of the respondents were not in traditionally computational domains. We have majority of the respondents are life sciences, and then we also have a lot of people in psychology, physical sciences, social sciences. There's a pretty big spread here. And so that means that we have a lot of people who probably are receiving some programming education, but not, it's maybe a minor part of their training. And I don't know if this is biased a bit because of the University of Michigan has a very large medical school, and so it might be overrepresented compared to at other universities. But just something to note, we're seeing a lot of uptake among people who are in not necessarily traditionally computational domains. Another finding, which I didn't fully expect, but actually completely makes sense, is that it was fairly normal for respondents to be programming in multiple languages. A slight majority of respondents are using more than one programming languages, and the median number of languages is 2, and that's going to come back in a minute. So I followed up with a few people from this study, just trying to pick based on interesting use cases that people mentioned in open-ended responses. And so I conducted some semi-structured interviews trying to get at the questions, what do scientists use code LLMs for, in their own words? And how do they think about verifying generated code? And just to note that when I ask someone, how do you think about this? That means that we don't have direct access to what they did in the moment. This is a self-recollection. So following up 14 interviews, and 10 of them were able to supply user logs. So that was screenshots of their chat logs, which was super helpful to cross-reference between what they're saying in interviews and what we can actually see in their interactions with specific tools. So what are they using code LLMs for? Well, the dominant use case that emerged is that these tools facilitate information retrieval when working in unfamiliar programming languages and libraries. Let's unpack that. Here's kind of an example quote that really exemplified it. Every question that I have, I put into ChatGPT. whether it's how do I extract a variable in a column to do X, or much more complicated tasks such as how do I adapt the format of a graph. And why do people need this? Why are there so many language changes that they're responding to anyway? Why are they working in so many unfamiliar languages? Well, it seems kind of baked into how a lot of people progress through their careers. When people change labs, they will often switch from one software toolkit to another. They will often have to work with legacy code, so there could be code left behind in, for example, Fortran by a previous student or postdoc, and so they will have to work with that code base. They may have to collaborate with someone who has a more limited set of tools available to them, who isn't comfortable learning a new language. So they may decide to use the language that is going to be the most accessible to everyone, even if that's not necessarily what they would use on their own. There's also specialty tools. So there's a lot of people who will say, hey, I need a very dedicated set of tools for my browser-based data collection, but I don't want to analyze my data in that same language. I'm going to switch some to like maybe R or something for my data analysis and visualization. There's also changing field norms. So, people make intentional decisions that they are going to migrate away from, closed licensed languages like MATLAB to, something that's fully open source and free like Python. And so people do make deliberate changes based on what they perceive as, changing field norms, and they have to adapt their coding to it. So it really does seem that people are often saying they'd rather use ChatGPT than the docs, and that's not terribly surprising in some ways because that's often what we see among professional developers too. They say it's a replacement for Stack Overflow. So here's one quote from someone who is a quite seasoned developer who said ChatGPT is just 1,000 times easier than documentation, just ridiculously easier. And another quote I found really interesting from a programmer on the complete other end of the experience spectrum who, came into the lab not knowing how to do any programming and had been there for a year and said, until I had enough coding experience, I didn't even look at the documentation because I would open it, read it, and there were so many words that I didn't understand. So I just closed it. But these days, I also don't read them because I realized I can ask ChatGPT to read them and then apply the information to my code. So how do these scientists verify generated code? Most of the people that I interviewed expressed confidence that they could catch errors in generated code through informal strategies, mostly forms of eyeballing, which people would say I'm eyeballing it or I look at it. And I wish I knew more about what specific cognitive activities that involve, like what are they looking at? But it does seem that it's a kind of visual inspection of the code, possibly running the code and then inspecting properties of the output, but not very much in the way of systematic testing, which is probably to be expected because if this is not a group of programmers that typically use a lot of forms of testing. And interestingly, even though I didn't really go looking for, errors intentionally, through the user logs that I was able to see, there were a number of cases where there seemed to be a verification failure happening. So some examples of these are, for example, one participant had actually copied the methods section of a paper and was prompting ChatGPT to produce a function that would correspond to a signal processing, step in the paper. And it did produce code, but it had the wrong parameters for smoothing, and it had faulty logic that led to an event deduplication step that would never actually be run. It would actually never be triggered. Another thing was people might put in two versions of code, so perhaps two different versions of the same, code base that they had found around the lab from a student who had left, and asked ChatGPT to explain the differences between the two code versions, and the explanations in this case, just visible in the logs, were not correct. They did not actually correspond to the real difference between the two programs. And another instance was somebody had put in a bunch of like a fairly long function, about 200 plus lines of code, asked ChatGPT to add a feature. And then it had, in addition to adding that line, had also removed other code that the user didn't intend. They did actually catch this one a bit later because of it messed up their instrumentation. It prevented their camera setup from running because of that was part of the code that had been removed. So they did eventually catch it, but they didn't catch it at the time of inspecting it. And I do want to point out that in none of these cases do I know that these, verification failures in the code would have corresponded to a major scientific issue. For example, if you have a function for time series, smoothing maybe, and you ask ChatGPT to write you something that, smooths with a window size of 100 milliseconds, in theory, hopefully it doesn't critically depend on if it's 100 milliseconds or 101 milliseconds, right? If getting the parameter wrong in a very minor way completely changes your result, that actually means it's not a particularly robust result. But we don't know here what was going to be the kind of the downstream effects of these unintentional coding decisions made by the model. An additional finding is that some participants seem to have incorrect mental models about what tools we're doing. So because we have the user logs for specific models, and a lot of them are using a model that was provided by the university, we can see what plugins or tools were available, whether there was actually any kind of web search available or not. And for example, there were some folks who described their tool of choice searching the web when it's not a tool that has web access, at least not advertised in any capacity or presented as, and something visible. Or describing a tool doing calculations or running code in models that, at least as advertised, have no code interpreter as part of them. And we can be sure, at least for the people using the University of Michigan tools, that these are not the case. So this just surprised me a bit. And that may just be because a lot of these interfaces are not especially clear to users where the answer comes from. It's just text. And so users may put a lot of high expectations on what kind of agentic actions like searching the web or running code are involved before an answer is returned, even when oftentimes it might just be a large language model doing its, large language model type operations. So another thing I did following up on this was in August 2025. So this just happened. I was interested in how does the perceived productivity that people feel with code LLMs relate to the actual development practices that they use? And I also wanted to find out who's not using code LLMs and why. And the reason that I got interested in this is that there was a fairly high-profile paper put out by a team at GitHub, Productivity Assessment of Neural Code Completion, and they have the real user data. I don't have access to people's GitHub Copilot logs. I can't get that, but the people at GitHub have this, so they could do a pretty cool study. And what they found, in short, is that when they survey early adopters of Copilot, and they assess them on a scale for their perceived productivity, it appears to be most associated with two factors. One of them is their programming experience. So people who are more junior programmers, the less experience they have, the more highly they rate their productivity with Copilot. And also the rate of accepted suggestions. So people who tend to accept more code suggestions from Copilot tend to feel more productive. And these things this could be a quite positive result that, people who are more junior benefit the most. And if they're really getting quality code out of this that serves their needs and they're learning, then maybe that's very good. And I think it's also open to the, more troubling interpretation that people who are less experienced are just less critical about what code they accept, and that leads them to feel more productive. So the work I'm going to present to you now is a collaboration with Jeff Carver at University of Alabama, Alexis Parker, who's a recent graduate in our master's program at the University of Michigan, and Nasir Isti at University of Tennessee, Knoxville. Jeff and Nasir are experts in studying scientific software developers, and Alexis is a programmer herself who contributed a lot of work on some of the qualitative coding of how, some of the data I'll show you. So the survey demographics are just, I was targeting this time any scientist who programs as part of their research, and I used mailing lists that were available through my professional network and my co-authors. We targeted a lot of people in the United States research software engineering community in particular. So those are people who, regardless of their job title, are spending a lot of time programming. And we also have a lot of folks from the University of Michigan because I have the easiest access to them. So N equals 868 here, but it is a mostly United States sample. And I'm assuming, I think this is fairly heavily skewed towards R1 universities. So asking people about how often do you use any generative AI tool in your research-related programming, adoption does seem common, but it's really far from total. I mean, the graph is actually somewhat symmetric, that the fraction of people who have either tried and given up or never tried is about the same as the fraction of people who use a tool most of the time or all the time. There are definitely field level differences. We see the highest adoption in the computer and information services field. So, these field labels are just from the NSF taxonomy for different research areas. It's possible they're imperfect. I just had people self-identify into what fit them best. And it's interesting. It's kind of computer sciences and then everybody else, and it's actually, that's the only thing that's significant is computer science versus everyone else, I think, if I'm remembering correctly. And so I'm not sure if that's because the other fields, maybe we just don't have as many people in them in order to resolve differences between some of them. I'm not sure, but that's what we're able to detect. We also see that students and junior programmers are most likely to use a code LLM often. So student researchers, we can see in the green over here. So student researchers tend to be the biggest users. And research software engineers, interestingly, are some of the least likely to, as well as faculty. And once again, chat is king. So asking about people's primary tool, the tool that they use most, overwhelmingly, people tend to use general purpose tools like ChatGPT or Claude or Google Gemini. A much smaller proportion are using a dedicated developer tool, a tool that is designed to work in your coding environment or a new coding environment that has, integrations throughout. Those would be things like GitHub Copilot or Claude Code, for example, or Cursor. So how productive do code LLM users feel, and what drives this? So using that GitHub study, we adapted their productivity scale, and we used a development practice scale. So this was basically, we wanted to find out, which of a couple of development practices are people familiar with and which do they actually use. So these are some development practices that are extremely common in professional software developing and have modest, familiarity to a lot of scientific software developers. So those are that we tested here: version control, code testing, code review, continuous integration. And these were among the most commonly known practices in one of the Carver studies of research software engineers. So that's why we picked these. So first we asked folks, are you familiar with these? And then we asked them, if they were familiar, how often do they typically use them? And then from those answers, we could create a composite score for each practice. And what we find when we make our big correlation matrix is that their composite perceived productivity score is actually negatively associated with every single practice that we ask them about. So just to highlight that here. So people who know about and use version control tend to rate themselves as gaining less productivity from a code LLM. The same with all of the kinds of code testing or code review that we ask them about. They all show a pretty consistent and very similar in magnitude relationship in the same direction. And we also see that programming experience is negatively associated with perceived productivity. So this was sort of interesting here. That's fairly similar to what the GitHub team found with their group. So I suppose this is a replication, but also a bit of a generalization because of our users are mostly using different tools. They're using more chat tools. They're not using, predominantly GitHub Copilot is not, anywhere close to the most popular tool here. So we're seeing something similar though. And I didn't fully expect this, but while modeling this, we can see that the effective programming experience interacts with users' development practices. So just doing a median split on development practice scores. So in the group with people with low use of development practices, there's a negative association between their programming experience and their perceived productivity score. So the more programming experience they have, the more their productivity score goes down. But in the group with high use of development practices, it's actually a pretty flat relationship. And if I had to make a post hoc hypothesis for what this is, my guess is that when you have those development practices in place, you get pretty rapid feedback about your code. Whereas if you don't have those in place to provide you feedback, I might guess you have to lean more on your own experience with your data and your models to kind of help you set expectations for how do I know when this is off. If you have a lot of experience with a certain data type, you know when something isn't coming out how you expect. But if you don't have that experience to draw from and you don't have other forms of feedback about your code, that might put you more in the area where you're rating your productivity perhaps higher than is warranted. And I also want to point out that, of course, even though perceived productivity might be less on average for people who are more experienced developers or who use these development practices, that doesn't mean those people do not feel more productive with code LLMs. On average, people are finding themselves more productive with them, and that's to be expected if they use them, right? We're asking people who use them. They generally do find it to be a productivity helper. It's just about how much perceived productivity. And so my guess, although I don't know for sure, my guess would be that people who are on the more moderate side are probably having a more realistic estimate of their productivity, whereas maybe if you're more junior, you just don't have as good a frame of reference. Kind of surprise finding is actually what was our biggest predictor of perceived productivity? Um, we had this question, how many lines of generated code suggestions do you typically accept at one time when working with this tool? And note that this does not mean that they don't modify the code at all after, right? So people could accept a lot of code, but still make changes to it. So we asked this question, how many lines of generated code suggestions do you typically accept at one time? And we find that the biggest predictor in our data set is this question. So the more lines of code people tend to accept from tools at once, the more productive they feel. And people who don't use it to directly produce code, but more to ask questions or do some kind of like lookup, about functions and a more, not asking for specific implementations tend to rate themselves the lowest. So generating more lines of code turns out to be a really big predictor. And so taking this as a whole, kind of the big takeaway is that perceived productivity with code LLMs is inversely related to code feedback mechanisms and experience. So why do people not adopt? I want to cover this real quick, just some interesting findings. We asked people who said that they had either given up on trying to use one of these tools or had never tried. Why do you think it is that you don't use these? And this was an open-ended question that Alexis went through and coded, and then I did a round of coding after, and we converged on these labels. And I just want to give a quick, breakdown of what are some of these themes here. Some of them I hope are a little bit obvious, but self-reliance is the first one. So that's when people really want to work on their coding skills and they're worried about short-circuiting their own programming skill development. So someone said, I've occasionally used them when I'm stuck, but I really want to improve my coding skills. And I think that the best way to do so is to write the code myself and work through the bugs. So that was our number one reason. There were a lot of ethical issues, and the ethical issues also themselves broke down into several categories. So I am generally opposed to generative AI because of concern over the ethics of the training of these models, stolen data, concern about the climate impact, And then also this person wrote concern over the accuracy of generative AI, like hallucinations or invented citations. So this is also about the accuracy of the model in addition to their ethical concerns. Another really common theme is that people did not feel they were saving time. So for people that are not adopting it, it kind of makes sense if they're making this time calculation, then it's not really worth it. So some folks wrote in, it takes more time to figure out what is wrong when I don't write the code. And that certainly corresponds with some findings from a variety of user studies of other kinds of programmers. So some conclusions right here. Adoption does skew junior in this cohort that we're sampling. The modal scientific programmer that uses an AI tool for support has a ChatGPT window open. They're not using a dedicated developer tool. It's probably ChatGPT, but of course it's not everyone. Perceived productivity looks like it indexes heavily on the generating code parts of development, not the other parts of software development. And this is just interesting because if anyone who's worked on a software project that's of moderate complexity, they often learn that writing the code is only part of the work. There's often a lot of work of managing complexity, of making changes while keeping the code working as you expect it to, about making the code useful to others, documenting it, and testing it, validating it. So making sure it really works how you think it does, especially if your code is, beyond the scale that you can just quickly eyeball and see that it's, how it's working. So this is, potentially quite, meaningful for what scientific work looks like. So let me unpack that a bit. What does this mean for science? And this is just kind of summarizing quickly some work that it's an opinion piece that was recently published in Nature Computational Science, and I'm happy to send you a copy if you email me. Code quality issues and concerns about this in science are quite old. A lot of scientific code is just hard to test. Sometimes we don't know what the ground truth is that we're supposed to be getting out of our systems. And that's because we're doing science and we don't know the answer in advance. So there are some real challenges in knowing, well, how would I even test the code that I'm writing to make sure everything is correct? We know that adoption of software engineering practices is inconsistent. And this can be because of, not every practice is a good fit for every lab, every research group, every field. So of course, some of that is to be expected. But adoption of practices is still fairly low, even though there has been some really fantastic work. I mean, I've seen a lot change over the time, that I started my training until now. There is, a lot of outreach and a lot of grassroots movements to improve the quality of scientific code, and it's made amazing progress. But it's, it's just still an inconsistent kind of territory. There's also a longstanding tendency towards trusting without verifying, and this is known not just for scientists, but there's a field of studies about spreadsheet programmers, which is kind of the ancestors of data scientists, where these are people who program in spreadsheets like Excel, and there tends to be signs of overconfidence, of accepting that if a number is produced through a series of spreadsheet calculations, the number is probably correct, rather than going through and testing all the steps in the spreadsheet calculation. So if these issues have been here, what is new exactly? Like, isn't it all just the same? So I would argue that there used to be a barrier to using code for science, and this was very much the case when I did my PhD. And it was that if you couldn't make code run, you couldn't use it to do science. So I remember that, when I got to the lab, a lab here, and I started out, there was a code base in the lab, and it had been used by many researchers before me. And my job was to get a copy of the code, get it working on my computer, and then run it with a couple different sets of parameters, and see if I could replicate what had been, published in some previous papers. And so if I could not make that code run, I was never going to be able to use it to run more simulations that I could eventually publish something about. But with the tools we have today, they do show a fairly compelling pattern that they are very good at making code run. You can very often brute force debug past an error in your code and make something that will run and will produce a number. And that's good in some ways because for a lot of junior programmers, those early bugs are super frustrating, super demoralizing, and a lot of people do spend months on them. But it also kind of puts you in a harder position because now you have code that runs, but you haven't learned very much about why it works. And catching these kinds of errors generally seem to be harder. So it's sort of like we've speedrun people into the hardest kinds of debugging problems. It's always risky, right? When your code runs, but the error is quiet, and that's sort of where we're putting them. If we bypass all of the learning that goes through, figuring out why code doesn't run in the first place. So more runnable scientific code, so something that does produce a number at the end or whatever you were expecting to get out of it, contributed by more people could strain our existing quality control mechanisms. This would be my worry. And on top of that, with more subtle errors than we are used to. So when I say this, the most common thing I hear is, so what if we all publish our code? And I think that is so nice in theory, and we should publish our code, but I don't think this will fix this particular problem. I think it fixes other problems. So when we look at what happens to code after it's posted online, most published scientific code repositories are not showing signs of reuse. So they're not showing a lot of interaction after the fact on GitHub. I can't completely resolve it, but I think the median number of stars on a published GitHub repository for a scientific paper is 0, I think. We're not getting a lot of forks or stars or interactions. And can we correct the literature when errors are found after the fact? So we can look at, maybe the Retraction Watch database, which is, to my knowledge, it's a really incredible tool if you haven't seen it, but it's a database collecting all of the retractions that have happened, I think in any field or area, anything that has like a DOI or a publishing index. And so there are 66,962 retractions as of a couple weeks ago. How many papers do you think there are? That it's actually hard to get an exact answer, but on Science's website, and this was in 2023, they were citing a number in 2022. That number had jumped to about 2.82 million papers. So there's a lot more papers, orders of magnitude more papers than there are retractions. And of course, that is to be expected because of most papers we think are probably not retractable, but it's still a disparity that I don't think those line up. And also, I want to point out how slow this process is. So this is a paper that was in JAMA. This is about long COVID or post-COVID-19 condition in children. And they found a very low incidence of long COVID in their study, so strikingly low. And then we get a retraction about this, saying that it turned out it was a coding error that had misclassified data points. And so, in fact, the incidence of long COVID was about 3 times higher than originally estimated. And how long did this take to be issued as a retraction? This is almost a year. That's fairly slow for, correcting a rather serious public health issue. And of course, this is nothing against this team here, right? This is the system that we're all working in, right? It's not possible. It's anybody could have a mistake in their code, and the retraction process can just be rather long to uncover this. And what else was I going to say here? Yeah. So this was just rather serious. So I would argue that we don't have a scalable, fast mechanism for correcting serious code issues in the literature when they happen. It's just not fast. Oh, I remembered what I was going to say. I was talking to a colleague who's a data engineer at a famous shoe company in Portland, and he was telling me that when they deploy a model and it fails, you get feedback within hours. You know that night that you shipped something that doesn't work because you start to see it in your sales data. And so there's really, like, this is fairly unusual in a lot of ways to work on a system where the time to detect and respond to errors can just be so slow, right? A lot of things in industry, you get much faster feedback because if it's something that has immediate use, things will be affected and you will notice. So I think papers, because if they often are not immediately, reused, or at least their materials aren't, it does really slow down the timeline. So I want to talk now about three bad scenarios that could happen, but I think none are inevitable. And I don't think these are, it's possible that these are not even, they may not come to pass because of various deus ex machinas that could happen. It's always possible, I suppose, that somebody could come up with a really radical innovation in how these models work. And so the kind of errors that I'm describing are going to be obsolete in a year. That could absolutely happen. But barring a situation like that, the first kind of bad scenario I worry about is that the quality of the scientific literature slowly and quietly degrades. So this is that, you know, if we don't have very strong feedback mechanisms or quality control on our code in the first place, and people continue working as they do, except, more and more folks are quietly working with code that they don't understand what's in it because they've used ChatGPT for most of it, or even just a fraction of it, but maybe a very critical part of it. Slowly the conclusions that rest on that code in the literature could, those could accumulate. We could have an accumulation of errors, but it might take us years to notice if a substantial portion of the literature becomes really, on very shaky ground. And I expect that this would be worse in fields where software development practices and reuse are uncommon. The more reuse you have, the more likely someone else is to look at your code and go, hey, why is this written that way? And that will start the discussion about, does it really match your intentions? But when we have code that just sits for a long time, unreviewed by any other person, untested, kind of ungrounded, that's more of a risk for where these kind of issues could accumulate. I'd also be worried about de-investments in scientific software. So if people tend to feel that they're very productive when they don't have signals about code quality, and there's very few visible consequences of failure, then that could lead to the value of software craftsmanship becoming obscured. So we could see de-investments from coding education, de-investments from our research software infrastructure and the people who maintain it. So that could look like assuming that, we don't need any of that now that ChatGPT is here, and beginning to make cuts without any immediate term, like short-term signal that that's actually perhaps quite risky for our software and our literature. I also worry about kind of, in an extreme case of a public trust crisis waiting to happen. So, I mean, could you imagine a high profile paper about a topic like vaccines or global warming? It gets covered in the New York Times, and then someone goes to the GitHub repository and realizes that the code is really poor and that it looks like it's just hundreds of lines straight out of ChatGPT. I mean, if that happened, that would be just a major fissure in public trust. And, there already are tensions like this. This is an example of, this is from 2020. So during the, early pandemic, this is Imperial College London had published some of their code that was about, it was a simulation of the COVID pandemic spread using a fairly famous class of models from epidemiology. And so, in fact, in that case, this is an example where it's such a well-established class of models that even though the code is not tested in a software development style, I do think there's actually quite a few quality checks built in because of kind of, it's very well studied at this point. It's not exploratory code. But a lot of people online noticed that this code base was released without a lot of built-in quality control checks. There weren't tests, and it received a lot of traction and a lot of anger from people who are saying that this isn't up to the standards of the kind of commitment to testing that we need. We need to really be sure if we're going to make decisions that change people's lives. And it's also possible this is just the attack vector, that maybe these are people that already felt very strongly that they were opposed to a lockdown. And this is just the vector along which they chose to kind of levy their arguments. I don't know enough about this to say, but it certainly, if that's your argument, that's possibly going to persuade a lot of people on the internet that this is not trustworthy. So moving away from the really scary stuff, what opportunities are there? So what can we do? I'd ask, are scientists using the best tools for their job? If people are using ChatGPT most of the time, that it sure is accessible, but it really doesn't have a lot of guardrails on what you can ask for or what you can do. So could we be quite imaginative about what would be an alternative? Also, because people regularly have to work on code translation or navigating between unfamiliar languages, could we develop more intentionally for that specific pain point? And I do think most AI products that tend to work are those that are really thoughtful about what problem they're solving rather than trying to be a general purpose kind of everything machine. So I'm interested in what's possible there. I also want to ask, how much corporate dependence are we comfortable with? I mean, you'll notice that most of the tools people are using those are provided by a small number of companies. There's not a lot of diversity in the sources of those. And I mean, really, in theory, any day the price of ChatGPT could be jacked up and then everyone's locked out. So are we comfortable having this much dependence as scientists on these corporate tool providers? And finally, I just want to think, even though we're talking about software here, how do we ensure the quality of the scientific literature, right? Because really what we're building towards is knowledge, right? We have code is one really important thing, right? And a lot of software projects are, they are the first products. But a lot of code is in the service of, creating conclusions. So in those cases, how do we ensure the quality of the scientific literature, not just the code? So let's have some questions, ideas. I thank you very much.